Hi everyone! It was a long break and a very busy time. Despite that, I have found time to record and make this repair video for you. Today on the bench, we have an unusual and super gaming AM4 motherboard, which was very expensive and popular 5-6 years ago, but is also competitive nowadays. So please welcome MSI MEG X570 ACE. This is a very beautiful motherboard. I have visited MSI website and read about this motherboard, and I can share some information which I guess is worth noting about its functionality. VRM is controlled by an IR35201 controller which generates 6+2 PWM separate signal lines. 6 lines from the controller goes to doublers, which are located on the back of the board, and thus we got 12 V-core phases and 2 PWM signals specifically for SoC. So almost all VRM uses power components of the manufacturer named International Rectifier. Their chips are usually marked with IR. So our doublers, for example, are IR3599, which seems to be working on 400 kHz frequency. MOSFETs are from IR3555. Those are the 60 amps power MOSFETs, which produces 1.2 volts of V-core, which can be measured after coils. The motherboard has only 4 SATA ports, which is very unusual, but it has a 2.5 gigabit Ethernet controller on the board, which is pretty impressive for a motherboard made 6 years ago. So we have this one gaming beast, which does not post. The CPU debug light is constantly on and it shows 00 debug code. This is the information of the customer. I have not tested it yet, and I guess this is the time to start with resistance measurements. Let's measure the resistances on the main power lines. We're going to use the ATX24 main power pin connector. And the first power line is going to be 3.3 volts, and we have 147 ohms. 5 volts, we have 500 ohms. 12 volts, here we have kilo ohms here, minus 12, no short, we have mega ohms. 5 VSB, 5 volt standby, and 855 ohms, which is normal. Then we'll measure 12 volts CPU, and here we have kilo ohms, so there's no short. Then we'll measure 12 volts to V-core, something right here. We have mega ohms, and the V-core itself, 120 ohms, which is normal. So all resistances are quite normal, and I guess we can try to install our testing CPU and try to power it on. Okay, so today we're going to use Ryzen 3 Pro 3350G AM4 CPU. This is going to be our testing CPU. And DDR4 memory. So A1, A2, B1, B2. We will use A1 just for testing purposes. Go here. We don't need a power button since the motherboard has its own power button right on the PCB. And let's power it on. So we have 154 milliamps of consumption. I see that the power button is illuminated, which means that it's powered. So let's try to press it. Reaction. And we have just 470 milliamps. It means that the V-core is almost certainly is not powered. And so we have the same situation that was described by the customer. If we're pressing reset, nothing happens. Do we have a reaction on the power button to switch it off? And it seems we don't have. So the next what I would like to do, reset the CMOS battery and to check if the battery is actually working or not. For that we're going to use the intelligent tweezers from NERC. Okay, what do we have here? We have 3.5, okay, 3 volts. The 3 volts is normal. So then what I would like to check, can we reset CMOS? There should be some headers for that. Okay, so we can clear the CMOS by shorting those two, I want to say pins, but not pins. They're not soldered in, but we can just short those two pads, which are exposed near the battery. This will reset the CMOS. So, power it on. Pressing power button. And I guess we have the same situation over here. Okay, so we have confirmed our customers' concerns about this motherboard. We have the CPU debug light on all the time, which means that we have stuck at the end of the power sequence. This kind of behavior may have different reasons, like trace broken, knocked off resistor. So I would start with detailed visual inspection under the microscope. If that will not reveal any issues, we'll go to BIOS and try refreshing it with the programmer. This is my plan. Let's follow it. And I need to remove the heatsinks. So we are going to start from the SIO area, and the SIO area, which is covered by a plastic from the heatsinks, looks normal. I don't see any blown components or knocked off resistors here. Then we can go to the RTC area. This is where the battery is. Right here you can see there's a two paths. You can short them and clear the CMOS. Okay, what else we have here? Those are the fans, fan controllers, buttons. Looks normal. Okay, let's go. This is an Ethernet controller. This one, 8125. So the VRAM area. Those are the MOSFETs. It's 3555, IR 3555. All of them looks normal. So those are the VR controller, IR 35201. So we have two marks. One mark is because it was pre-programmed during the manufacture. Another one is probably a quality mark. So those two lines are SOC lines. Other lines are vCore accordingly. Okay, let's go to the PCH. I just turn it around. And what do we have here? Nothing critical in the PCH area. Those are the main power connector. Let's go to the back of the board. And we have a lot here. We have a lot of components. So this is under the VRAM area at the bottom of the board. So you see the doublers are here. Doublers and filtering caps. Okay, this is a CPU area. This looks fine. Those are some inductors, the caps for signal pairs, some damage to the traces, but I'm not sure. I don't think it's broken. Okay, so it looks like I need a board viewer schematic for this board, since I don't see any obvious damage or failed components. So let's try to measure the resistances on the coils. Okay, the PCH, just 5 ohms. That could be a problem. Let's try to measure voltage when we power it on. Okay, pressing the power button. Okay, 281 milliamps. This is probably because we don't have RGB lights and we don't have a fan for PCH cooling. This is the problem. It could be a dead PCH. So let me show you the diagnostic path I followed to find the root cause of this issue. I will go through it step by step so you can follow along. I started at choke 24 where I measured the chip SoC line. This is the 1-volt power rail for the PCH, and it was dead, no voltage. So clearly something in the power sequence has failed before this point and I needed to trace it back. The next step was to look at U55. This is the regulator which is supposed to generate the chip SoC voltage, and the reason it has no output is simple. It has no enable signal. Chip SoC enable is low, the IC is just sitting there doing nothing, waiting for permission to turn on, so I need to find out why chip SoC enable is not being asserted. Tracing the chip SoC enable signal, I found that it depends on CPU 1.8 volts power good, the power good signal for the 1.8 volt CPU rail. This signal passes through transistors Q63 and Q72 before it reaches U55, and it is low. So the 1.8 volts rail either has no come up or its power good signal is not being generated correctly. Let's keep going. Now I looked at U40. This is the regulator responsible for the 1.8 volt CPU rail. And the problem here is the enable signal, CPU 1.8 enable, is low. U40 has never been told to turn on, so I need to understand what is supposed to drive this enable signal and why it is not doing so. The CPU 1.8 volts enable signal is controlled by DDR power good, the DDR power good signal which passes through transistors Q69 and Q70, and this signal is also low. This makes sense. The board follows a strict power sequence and it will not enable the 1.8 volt CPU rail until it knows that DDR memory power is stable. So DDR power is clearly not up. Let's find out why. DDR power good is pulled up to the 5 volt DIMM rail, and when I measured 5 volt DIMM, it was essentially dead, just 0.2 volts, not even close to the expected 5 volts. So the DDR memory has no power at all, which explains why the entire power sequence above it has stalled. Now the question is, what is responsible for generating 5 volt DIMM? And here is where it gets interesting. Tracing the 5 volt DIMM circuit, I found Q15, an N-channel MOSFET. When I touched the probe to measure the voltage in this component, I noticed that it was physically lifted off the PCB, just sitting there, not making proper contact with the pads. No soldering, no connection, nothing. 7 stepped in the fault chain, one bad component at the bottom of it all. This is exactly why we trace the power sequence properly, because the symptom and the root cause are almost never in the same place. So let's replace this component by salvaging it from a donor board. Okay, so let's shield it. Oh wow. When I started to applying heat with my hot air gun, and the component just disintegrated right in front of me, the package completely fell apart and you can actually see the semiconductor die exposed. the bare silicon sitting there in the open. This component was completely destroyed internally. Okay, let's power it on and to see if we have succeeded in this repair. Okay, so CPU in place, memory is in place, power on. We have 150 milliamps and pressing the power button. And as you see, so we have a CPU, debug LED, we have debug codes running here, and I guess I need a heatsink. Okay, so the capture screen is here, the GPU is here, heatsink for the CPU, DDR memory, power on motherboard, and pressing the power button. Okay. So we have postcodes. Will we have a post screen? Okay. 2.4 amps. Come on. Will we have a post screen? VGA. Boot. And yes, we do. We have a post screen. This is fantastic. Okay, let's see what we have in BIOS. Nice date. It's 24 July 2036. And the BIOS build is 2020. It's kind of outdated. We will update it for sure. But it was very unusual fault with that. So this is it. This is how we repaired this beautiful and not cheap at all MSI MEG X570 ACE motherboard. And I have to say, this was a very unusual fault. In my practice, I have seen many different failure modes: burned MOSFETs, dead controllers, shorted capacitors, broken traces, but a MOSFET that has simply lifted off the board, this is something I have not seen before. Most likely this component was defective right from the factory and failed at some point during the life of this motherboard. Over time, the thermal stress was enough to destroy the component and lifted it completely off the pads. I hope the repair path was interesting for you, and I would love to see your questions in the comments. I always try to answer all of them, and I'm so glad to see so many positive comments from you. Thank you. Please do not forget to hit the like and subscribe button. Thank you for watching, and I will see you in the next one.